Good morning, everybody. Hope you're all healthy and safe at home. We are going to begin with section 9.5 of our module. This section deals with the concept of directional derivatives. So, we had seen that in the previous section we have discussed about partial derivatives, and we also know that the derivative is actually the slope of the tangent to the curve at a particular point. So how can we introduce this same concept to the partial derivatives also? So let us see. We are given a surface, say z is equal to f of xy. Okay. In that surface, you can see, just look at figure 9.5.1. We are considering the surface z is equal to f of xy, which is the blue shaded portion. That is the surface which we are having it. And if we consider vertical planes which are parallel to the x-axis, and so we are considering a plane in this direction and another plane in the direction which is parallel, or in the a plane which is parallel to the y-axis. So when we consider these two planes, they will be actually cutting the surface at this point and at this curve. So when that plane which is parallel to the y-axis cuts the surface, we'll get this curve, and when the plane which is parallel to x-axis cuts this surface, we get this curve. So we are having, again we are moving on to the concept of curve and a point, and we can clearly discuss the slope of the tangent at a particular point in the curve. Now, so we can think about dou z by dou x to be the rate of change of f in the I direction, and dou z by dou y can be considered as the rate of change of f in the j direction. So next we will think about what will be the rate of change of f in this particular direction when we are considering the function, that is the surface. So we can think about any direction, can be in this direction, any direction which is tangent to this particular surface. So that is how the concept of directional derivative comes up. So we are going to find the derivative in any particular direction which is given to us. So before that, we are going to introduce a new differential operator, vector differential operator, that is del is equal to I into dou by dou x plus j into dou by dou y, or in case of three variables, we have del is equal to I into dou by dou x plus j into dou by dou y plus k into dou by dou z. So when we are considering the functions, differentiable functions, z is equal to f of xy or w is equal to capital F of xyz, we will say that del of or gradient, this is actually called as named as gradient of f of xy, which is equal to dou f by dou x into I plus dou f by dou y into j, and gradient of f of xyz is equal to dou f by dou x I plus dou f by dou y j plus dou f by dou z k. Actually this is the not a del, it is inverted del, it is a Greek symbol, and along with f of xy together we call it as the gradient, grade f, and these are the gradients of the given function. This value is called the gradient of the given function and it is pronounced as grade f. So let's see an example how we can calculate the gradient. It is easy. You can see that we have to compute the gradient f of xy. For f of xy is given to us 5y minus x cube into y square. So what we have to do, we have to first partially differentiate the given function with respect to x, keeping y as a constant. What will be it? It will be, this will be 0 and this will be minus 3x square y square into I, and dou by dou y of this function f of xy, that is 5y minus x cube into y square into j. That is, we have to partially differentiate the given function with respect to y, keeping x as a constant. What will it be? It will be 5 minus 2 into x cube into y. So that's how we calculate the gradient. In the next example, it depicts how to find the gradient at a particular point. That is, we are given a function and what will be the gradient at the particular point which is given to us. So if you see this example itself, what will be the gradient of f at the point say 1, 1? We just have to substitute the value of x and y to be 1. So it will be minus 3i plus 5 minus 2, that is 3j, that is minus 3i plus 3j. So in this example, let's see. We are given f of x, y, z is equal to xy square plus 3x square minus z cube. We need to find the gradient at the point 2, minus 1 and 4. So the gradient is dou by dou x of xy square plus 3x square minus z cube into I plus dou by dou y of xy square plus 3x square minus z cube into j plus dou by dou z of xy square plus 3x square minus z cube into k. So what will be the differentiation? Derivatives, partial derivatives. The first derivative with respect to x will be 2x y square, y square plus 6x. The second one would be 2xy. That's it. The rest are constant. And the third one would be minus 3z square. So that will be our gradient grade of, that is y square plus 6xi plus 2xyj minus 3z square k. Now what is the value at 2, minus 1 and 4? You just have to substitute the value of x, y and z, 2, minus 1 and 4. So that will be 39 minus 4j minus 48k. So next we are moving on to the definition of directional derivatives. So first let us see, in the beginning of the session we had said that we are going to find the derivative in any given direction. So here we are going to consider any unit vector, say u is equal to cos theta I plus sin theta j. That is the most general form of a unit vector because the magnitude of u will be 1. And we are going to consider another vector which is parallel to this vector u. Okay, and this vector is considered from the point xy0 to x plus delta x, y plus delta y comma 0. This is the vector v. You can see it in the figure 9.5.2. Now, if h is equal to root of delta x square plus delta y square, then we can consider v is equal to h into u. Okay, so here we have this blue shaded portion is the given surface. Now, if we consider this plane, this is the rectangle is the plane. If we consider this plane, this is cutting or it is slicing the given surface and we form the curve. We get the curve C. So now we are going to find the tangent at the point P to the curve C in the direction of U. Is it clear? We are going to find the tangent at the point P to the curve C in the direction of U. Now from the figure it is clear that this delta x is nothing other than, this is the angle theta, this is the change in x, that is x is moving from, we are moving from x to delta x, this is the change, and this is a change in y, that is from this point we are getting to this point, so that is delta y. So we can see that delta x, if we consider this triangle, it is a right angle triangle, so we can see delta x is h cos theta and delta y is h sin theta. Okay, now so we can find the slope of the indicated secant line will be f of x plus delta x comma y plus delta y minus f of xy by h, which is equal to nothing other, we are going to substitute the value of delta x and delta y, f of x plus h cos theta comma y plus h sin theta minus f of xy divided by h. Now, if we apply limit h tends to 0, this will give us the equation of the slope of the tangent at the point P to the curve C in the direction of the unit vector u. So, this is how we are going to define our directional derivative, that is the directional derivative of z is equal to f of xy in the direction of a unit vector u equal to cos theta I plus sin theta j is, it is denoted by du. Okay? Du of f of xy equal to limit h tends to 0 f of x plus h cos theta comma y plus h sin theta minus f of xy by h, provided that this limit exists. Now in the previous section we had learned about partial derivatives. So this directional derivative is nothing other than the generalization of partial derivatives. How can we say that? See, if the value of theta is 0, what will happen to in this derivative? Cos 0 is 0 and sin 0 is 1. So this will become limit h tends to 0 f of x comma x plus h comma y minus f of xy. That is, y is kept constant and there is a variation in h. So that is nothing other than the partial derivative of f with respect to x. Similarly, if theta is equal to pi by 2, what do we get? Cos pi by 2 is 0 and sin pi by 2 is 1. So we get this directional derivative will become limit h tends to 0 f of x comma y plus h minus f of xy by h. That is nothing other than dou z by dou y. So this is the relation between the directional derivative and the corresponding partial derivatives that we had discussed in the previous class. So now we can, this is a bit complicated formula to find the directional derivative. We are given a vector and a unit vector, then we have to find the directional derivative. So in the next class we will discuss how we can relate the gradient and the directional derivative. We had learned what is the gradient of a function in the beginning of this section. So in the next class we shall find a method to find the directional derivative using the gradient of that function. So that's it for today's section. Thank you. Stay home and stay safe.